So in this little lecture we're going to talk about waves in 2 and 3 dimensions. Previously we talked about just one-dimensional waves, and we looked at a sine function for the shape of the wave. But waves can have just about any shape you can imagine. The sine function is nice because it's pretty easy to work with, and there's a lot of good real examples that are very close to actually being sine waves. But now we want to be a little more realistic and talk about waves that don't just travel in one direction, left, right, or up and down, but rather waves that travel on a surface, like the surface of a pond, or that travel in 3 dimensions, like sound waves coming from my mouth, or sound waves coming from a horn, or your speakers in your stereo, or light waves that travel from a star and go in all different directions. Those are more than one-dimensional waves. Those are 2-dimensional, 3-dimensional waves. So what we need are some coordinates in 2 dimensions. In 1 dimension, we just had like an x direction to describe position, or a y direction. So depending on what direction the wave was moving, we called that direction some coordinate x or y or z or something. That's all we needed, and then we needed time. But now we have, if we want to talk about 2-dimensional waves, we need a surface. So if we think about waves on a flat surface, like the surface of water, or waves on the surface of a drum, or waves on anything that's sort of 2-dimensional, we would need 2 coordinates, an x and a y coordinate, or maybe a y and a z, or an x and a z, depending on what coordinates you are laying out on that 2-dimensional surface. If we have 3-dimensional waves that can travel in the whole 3 dimensions of space, then we would need more than 2 coordinates. We need 3 coordinates. The types of waves that we might be talking about are pretty much anything. In reality, really, pretty much all waves travel in 3 dimensions because we live in a 3-dimensional world. You can, in certain cases, restrict waves to travel in 2 dimensions. So like the drum head is a good example, a nice membrane. The membrane of the drum is a pretty 2-dimensional thing, and the waves on it travel in 2 dimensions across the drum. But sound is kind of hard to restrict to 2 dimensions. It's pretty much a 3-dimensional wave that travels out in all directions through some space, whether it's the air in the room, or it could be a cavity in a musical instrument that the sound is traveling through. All those things are 3-dimensional things. So it's actually kind of hard to find waves that are not 3-dimensional. Earthquake waves travel through the earth, water waves under the surface, and so on. So we need coordinate systems. We need 3 variables, typically either x, y, and z, or depending on the shape of the wave, it might be more convenient to use spherical polar coordinates, r, theta, and phi. So it just depends on how you can describe the wave most easily mathematically. What is the shape, and which coordinate system best describes that shape in the simplest mathematical form. So we're going to talk about circular waves to be sort of simple. Waves that travel in 2 dimensions or 3 dimensions can have all kinds of crazy shapes to them. We're going to look at 2 special shapes. In 2 dimensions, we're going to talk about circular waves. So this is like what you might see on the surface of a pond. You might see a rock dropped right in the center, right here where it says source, and little ripples on the surface of the water travel outward at some velocity v. And as they travel outward, you can see the maximums of those ripples form these circles on the surface. This little line right here kind of represents if you were to cut the water in a plane perpendicular to the surface and look at the water at an instant, you would see that in some places the water has risen up above equilibrium. In other places it's gone down below equilibrium and then gone back up over equilibrium, and so on. As the wave travels outward, the points on the water rise up and down, up and down, up and down, perpendicular to the surface. And so this little line here, this looks like a sine function kind of graph, is like a cross-sectional plot of what the wave looks like in one particular direction. And these circles that we've got drawn here are called wave fronts. They're drawn in such a way to represent all the locations on the water that are all at the same maximum displacement. We say that they're all at the same phase. We've used the sine function before to describe the displacement of the medium, and the argument in the sine function is often called the phase of the wave. And if there are points in space that have the same argument of that sine function, maybe it's a 2 pi, then those points have the same phase. The argument of the sine function is the same, and therefore the displacement of the medium is the same. So in the same sense, we're going to look at a mathematical function for these waves. We don't quite know what that is yet, but there's some kind of a phase of the wave. And all the points on a wavefront have the same phase. In this case, these wavefronts represent maximum displacements. The next wavefront also represents maximum displacements, but that would be a slightly different phase than this wavefront because we're further away. These wavefronts, we'll talk about this more in the next video, but these wavefronts would have a difference in phase of 2 pi. They're both maximums, but the whole function has gone through a cycle between one wavefront and the next. And so in terms of angles, in terms of arguments of the sine function, if it goes through one complete cycle, that argument has gone through 2 pi radians. And so the phase has gone through 2 pi radians and going from this wavefront to the next wavefront and to the next and to the next. But what's common about all these wavefronts is that they all represent locations in space where the amplitude of the medium, the displacement of the medium at this moment is a maximum. We could draw, and sometimes you see drawn, dotted lines, dotted circles between these solid circles. Those dotted circles represent minimums, places where the medium is a minimum. We don't have that here. We just are going to stick with drawing wavefronts that represent places where the medium is at a maximum displacement. So again, this is like a water wave where something has been dropped into the water, and these little ripples, these little disturbances travel outward like circles, and as time goes on they spread out. So this little wavefront will get further away, this little wavefront will get further away, this little wavefront will get further away. And as time goes on, they'll just spread out and eventually dissipate. There's some kind of friction, and so eventually the energy carried in these waves will be dissipated away. So that's a circular wave. One thing that you should notice is that in circular waves, what really matters is not what direction you look, but rather how far away you are from the source. So in other words, if I look off in this direction, straight up here, I see the exact same series of maximums and minimums as if I look in this direction down here. You see exactly the same thing. So the angular direction makes no difference. What's really important is how far away you are, the radial direction. That's important. So these are circular wavefronts with a certain wavelength lambda, and the displacement function, whatever the mathematical function is that tells you what the water's displacement is relative to equilibrium, it does not depend on what direction you're looking from the source. It only depends on how far you are away from the source. So what about three-dimensional waves? Well, that diagram above also represents, or also can represent three-dimensional waves. But in terms of what the shape really looks like, think about taking that two-dimensional picture up here and kind of rotating it around. These circles rotate into spheres. So a three-dimensional wave is a spherical wave. The wavefronts are spherical shells that propagate outward away from the source. Each spherical shell, represents locations in space where the medium has the same amplitude, the same displacement, I should say, at any given time. And we would have a set of concentric spherical shells spaced one wavelength apart, going from the source outward and traveling outward at some velocity v. And all those waves would all those wavefronts would all travel at the same velocity, and they would always be 1 lambda apart. And if this was a source in the middle that continuously gave off waves, you would see new wavefronts forming as time goes on, and they would continue to expand outward as all the other wavefronts expand outward. So for a three-dimensional wave or a two-dimensional wave, for circular waves and for spherical waves, this diagram works well. It represents exactly the circular waves on the surface, if you think about these circles as being the locations of maximum displacement, or it represents like a cross-section of a spherical wave where you're kind of slicing through all those concentric spherical shells of maximum displacement. So this little diagram down here shows that a little bit better. I've just colored some things here. I've got these circles that are different colors, red, orange, yellow, and then green and blue, purple, whatever that is. And I've drawn that sinusoidal function so you can see each shell, the boundary of each shell represents where the amplitude is a maximum above equilibrium. And then it goes down, then it comes back up again, and then down and back up. So as this wave is traveling radially outward, the medium is going up and down, up and down, up and down as this little white sine function or cosine function travels outward. But this is looking, this white line is looking in one particular direction. The thing to remember about about circular waves and spherical waves is that the direction doesn't matter. So I could just as equally draw this little sine function in any direction I want. I could draw it out in this direction, I could draw in this direction, I could draw it coming out of the board, I could draw it coming at some crazy angle up this way and out of the screen or into the screen. As long as it's coming radially away from the source, it looks exactly the same. The wave, the medium is changing, is vibrating in exactly the same way. So we can kind of see that if I take this figure and I can rotate it, you can see that what I have here really is not a bunch of concentric circles, but rather I have concentric shells. So we'll rotate this a little bit and you can see the shells kind of popping out there. And so inside there's a little shell, a spherical shell of maximum displacement. All the points on this red sphere have some maximum displacement. And then the points between the red sphere and the orange sphere go down, and eventually there's a region in between these two shells where the displacement of the medium is a minimum. And then as you get out toward the orange shell, the displacement of the medium is again a maximum. But everywhere on this orange shell, around this perimeter here, as well as around through the back here and out in front, I've kind of cut these spheres in half. Everywhere on this sphere, this orange sphere, the displacement of the medium is a maximum. And then you continue to move outward at this moment in time. All the points on this yellowish sphere are also all at maximum displacement. And same for the green and same for the blue. So all these shells, these spherical shells, represent locations of maximum displacement from equilibrium of the medium. So this could be a sound wave, for example. And if I've got a little tiny speaker in the center here, this sound wave could be, or the speaker could be vibrating, giving off this wave that travels out away from it in all directions. And any given instant in time, this could be what you have. You have a region in the air here where the pieces of air, the little chunks of air, have been pushed in the positive direction, outward actually. Remember, sound is a longitudinal wave, so if sound is traveling radially away from the source, the air is actually vibrating back and forth like this. So all the points in space along this red sphere, the air there would have been pushed outward a little bit. The air in this region in between the red and the orange is all at a minimum displacement, a negative displacement. Those would be all places where the air has been pushed inward a little bit, and so on. The points on the orange would be places where the air has been pushed outward, and in between the orange and the yellow is places where the air has been pushed inward, and so on. The air, as you move away from the source, or as you just stand in one point and let the wave pass you by, the air is vibrating back and forth like this. So it's a longitudinal wave. So whether you're talking about transverse waves or longitudinal waves, these shells represent locations of maximum displacement from equilibrium. And this is a representation of spherical waves. They form these shells of maximum displacement throughout all of space. So how do we represent this mathematically? Well, again, whether we're talking about spherical or circular waves, the only thing that matters is the radial direction, the radial distance, not direction, but radial distance. How far are we from the center, from the source? The direction that we are doesn't matter, because these things are circular or they're spherical, and we're assuming the source is at the center. So there's some kind of a function, a displacement function, that describes the displacement of the medium, and that displacement function is not going to depend on any angles, theta or phi, for example. Rather, it's going to just depend on our distance from the source. So we're going to call this thing d of r comma t. It's a displacement function that depends only on radius, and it depends on time, of course. And it's going to look just like, if we're again talking about sinusoidal waves. Again, we don't have to be always talking about sinusoidal waves, but we will continue to talk about them because they're good examples of things that can be used, and they are realistic. They're not perfectly realistic, but in reality we'd have to modify them a little bit. And in fact, we've made a little modification here. But we've looked at, we have a sine function. It depends on the radius. It also depends on time. There's a phase constant inside of it. There's a frequency multiplying time. There's a wave number, 2 pi over lambda multiplying the distance. And I've got a negative in here, too. And I'm not going to put a positive in here because we're assuming that the source is at the center of the waves, is at the center where r is equal to 0. when you're talking about radial coordinates, radius is never negative. Radius is always a positive thing. So if the source is in the center at r equals 0, the waves are always going to be moving outward away from the source in the positive r direction. So if I have a wave that's moving in the positive x direction, for example, I would have kx minus omega t. If it's traveling in the negative x direction, I'd have kx plus omega t. But these waves are not traveling in the negative r direction, they're traveling in the positive r direction. So it's kr minus omega t. And then also with spherical or circular waves, one thing that is true is that the amplitude actually is not a constant. It can't be a constant. These waves, you can think about each wavefront as sort of, in total, each wavefront is carrying a certain amount of energy. And we'll talk about power and energy in another lecture. But there's a certain amount of energy. And that energy is what's displacing the medium, pushing the medium away from equilibrium. And if that energy, if these shells or these circles of wavefronts are getting bigger and bigger and bigger, that energy is getting more and more spread out over that wavefront. And so the amplitude, the amount of push on the medium at any given point is going to be less and less and less as you go further and further away. So these amplitudes actually depend on radius. This is an amplitude that depends on radius. And the way this works, it could be in many different complicated ways that this amplitude is a function of radius, but in general, the amplitude I should say, goes to 0 as the radius goes to infinity. So the further away you are from a source of light, for example, from a source of sound, for example, it makes sense that the amplitude goes to 0 because the sound or the light is dimmer or quieter the further away you are. The amplitude is getting smaller and smaller and smaller because these are not one-dimensional waves. For a one-dimensional wave, if there's no friction loss or anything like that, that one-dimensional wave will have the same amplitude for all of the x-axis, no matter where you are, because there's no other place that wave can go. It's always going to be on the x-axis. For circular and spherical waves, that wave can spread out over the plane or over all of space if it's a three-dimensional wave. So this is a basic equation that we can think about to describe basic circular and spherical waves, because in both cases the wave only depends on the radius. It doesn't depend on the angles. And if we're talking about a sinusoidal wave, then we can use the sine function with some phase constant in here. The difference between circular and spherical would really come in how this amplitude depends on radius. In one case, the amplitude might depend on radius, say 1 over the radius. In the other case, the amplitude might depend on like 1 over the square root of radius or something like that. So there might be a difference in how this amplitude depends on radius, whether you're talking about circular or spherical waves. But in both cases, as the radius goes to infinity, that amplitude function goes to 0. The further away you get, the smaller the waves are. So if we do get far away, what do the waves look like? Well, if you think about spheres, if you think about a spherical wave coming from a source, if you think about light coming from a star, for example, and the star is really far away, this light is coming from the star and it's like a bunch of concentric spheres getting bigger and bigger and bigger, moving away from the star. Well, as you get further and further away, if you were sort of standing on one of these spheres, if you could somehow do that, as it gets further away from the star, that sphere would get bigger and bigger and bigger. The curvature of that sphere would get flatter and flatter and flatter. Just like the Earth. The Earth is not a really big object in terms of astronomical things. It's fairly small. But to you and I, we're just kind of standing on the Earth, it looks kind of flat to us. But if you backed up a little bit and looked at it from a distance, you would see that it's certainly spherical, or at least very, very nearly spherical. So if either you let the Earth get really, really big, or you get really small and stand on the Earth as a very small person like we are, the Earth appears to be flat. And so in the same sense, as you let these spherical shells of wave move further and further away from the source, these wavefronts that used to be spheres, or they still are spheres, but they're so big that they look nearly parallel to each other now. You can't really see the curvature of them anymore because you're so far away from the source, and they're all moving in this direction. These green arrows represent the direction. They're all traveling at some velocity v, and it looks like just a bunch of flat planes traveling away from some source farther over here to the left. It's hard to really tell that these are really spherical waves because the spheres are so big that the adjacent spheres are pretty much parallel to one another. In reality, they're not. They're still big spheres. They're just so big that we can ignore the curvature and just think about these as flat wave fronts. So we call these things plane waves. The word plane doesn't mean like airplane, it just means flat. So these are waves that are flat. And every point along this wavefront, again, the amplitude, the displacement of the medium is exactly the same. Every point along this wavefront, if this is the x-axis that the wave is traveling along, or you could call it the r-axis, then all these points perpendicular to that r-axis, or x-axis, on this line here, on this plane here really, all those points are, they all have the same displacement. The medium has the same displacement. All the points on the next wavefront, the medium again has the same displacement, but the wave has gone through a 2 pi radian cycle from one wavefront to the next, and then from this one to the next, and so on. So another way to look at this is with this plot here. Here are some plane waves traveling to the right, and we can again imagine these wavefronts, these shaded planes here. They're separated by a distance lambda, and these blue graphs represent the actual wave, what the medium is doing at any given location. So at x equals 0, for example, all the points on this plane have a maximum displacement from equilibrium. All these blue graphs are at a maximum. And then if we go to the next plane, all the blue graphs are also at a maximum here. So every single point on this plane is at a maximum amplitude. And then same as this one here. Every single point on this plane is at a maximum amplitude. We can kind of imagine maybe a dotted plane in between these two, where all the points on that plane would be at a minimum, a negative displacement from equilibrium. And so on. We can think about imagining all kinds of different planes traveling to the right as this wave is moving. In reality, there's just waves moving. There's sort of vibration moving, a disturbance through the medium. But these planes, they're not real. They're just ways of kind of drawing a place in space where everything is the same. So on every single plane here, everything is the same, no matter where you are. If this upward direction, let's just say, is the y direction, and the outward direction is the z direction, this is a plane that is in the yz plane, perpendicular to the x-axis. No matter where you go on this plane, and if you were to go anywhere on this plane and measure the displacement of the medium at this point in time, you would find that the medium has been displaced a maximum distance from equilibrium everywhere. And so if we think about a function to describe the displacement of the medium for a plane wave, that function is not going to depend on y or z, because it's the same no matter where you are on this plane in terms of the y and z directions. The displacement is only going to depend on where you are in the x direction. And so this is very similar to a one-dimensional wave. In the one-dimensional wave, the displacement only depended on where you were in the x direction. So we can think about a displacement function, again, for a plane wave that depends only on the x direction. The wave is moving in the x direction, and it can be represented by a series of wavefronts, but these wavefronts are all parallel to each other. They're all these flat planes, and it doesn't matter where you are in the y or the z direction, you always measure the same thing for any other point as long as the x value is the same. And so the displacement only really depends on x. And of course it depends on time too. And again, it's a sine function, and we'll assume the wave is moving to the right in the positive x direction, so we'll put a k times x minus omega t, and we have a phase constant there. But again, the amplitude could be changing. Again, because these are not true one-dimensional waves, even though this equation looks very much like a one-dimensional wave because it only depends on one variable. These wavefronts could be getting these amplitudes, these maximum displacements along each wavefront, could actually be getting smaller and smaller and smaller as these wavefronts move further and further from the source. And that's because the waves are really being spread out over 3 dimensions and not just 1 dimension, like a one-dimensional wave would be. So, we've seen this equation over and over again, the sine function equation. And it's interesting because it applies to not just one-dimensional waves traveling on like a string or something, but it applies to 2-dimensional circular waves if you replace x with r. And it also applies to 3-dimensional spherical waves if you replace x with r. And it also applies to 3-dimensional plane waves, spherical waves where you're really far away from the source. those wavefronts seem parallel, they seem flat. And so the equation that describes the displacement of the medium only depends on x, only depends on the direction that you're traveling, that the wave is traveling. Anywhere perpendicular to that at any given time is going to look the same. And then there's some possible differences in the way the amplitude behaves, depending on what kind of wave it is too. So this equation is very useful, this displacement equation with the sine function here. So definitely remember this, and we'll do some examples in class on using this and solving for some of the variables. So that's all for this little lecture. We'll talk about next time, we'll talk about phases. What does it mean? Again, what do phases mean, phase differences, and things like that. And then we'll be talking about power and energy and also the Doppler effect.